In this video, we will discuss the notion of linear independence. Suppose we have a subset S of a vector space V. We say that this set S is linearly independent if, whenever we take distinct V1 up to Vk from S, then if we are told that lambda 1 V1 plus ... plus lambda k times Vk is equal to 0, then we can deduce that all lambdas i's are equal to 0. And if this is not the case, then S is linearly independent. So it's going to be linearly independent if we can find V1 up to Vk in S and lambda 1 up to lambda k, not all of them equal to 0, such that lambda 1 V1 plus ... plus lambda k Vk being equal to 0. So for example, this set here is linearly independent because I can find such lambda i's. We can check that 3 times 1, 2, minus 1, 3, plus 2, 3 is equal to 0. So the set is linearly independent. And on the other hand, this set containing only the vectors 1, 2, and 1, 3 is linearly independent because if we are told that lambda 1 times 1, 2 plus lambda 2 times 1, 3 is equal to 0, then we can deduce that lambda 1 and lambda 2 are equal to 0. And the reason is because we are trying to solve this system, but this matrix is invertible, so by our standard arguments, lambda 1 and lambda 2 must be equal to 0. It is immediate from the definition that if we take any subset of a linearly independent set, then this is also linearly independent. Let's proceed with a couple of warnings. The first one concerns the case when S is equal to empty, and we claim that this set is linearly independent. So let's go back to the definition. We said that S is linearly independent if whenever we take distinct V1 up to Vk from S, and we are told that a linear combination of them is equal to 0, then all coefficients are equal to 0. So how can this fail? It can only fail if somebody can find V1 up to Vk from S, and he can find scalars lambda 1 up to lambda k, not all of them equal to 0, but with lambda 1 V1 plus ... plus lambda k Vk equal to 0. So it's important to be able to find these V1s up to Vk from S. But if S is empty, this is impossible. So it must be linearly independent. The next warning concerns the following definition in quotations of linear dependence, which is actually incorrect. So this possible definition says the following. It says that a set S, say V1 up to Vn, is linearly independent if we can find lambda 1 up to lambda n, not all equal to 0, such that lambda 1 V1 plus ... plus lambda n Vn is equal to 0. So this looks very, very similar to what we've been doing before. But what is the problem with this definition? The problem is the following. Let's consider the following set S. So it contains the elements V1, V2, and V3, where V1 is 1, 2, V2 is equal to 1, 3, and V3 is equal to V1 is equal to 1, 2. Now, according to this definition, here, this set is going to be linearly independent. Just take lambda 1 equal to 1, lambda 2 equal to 0, lambda 3 equal to minus 1. We will have V1 minus V3 is going to be equal to 0. But this set S is the set containing 1, 2, and 1, 3. And we have seen that this set is linearly independent, not linearly dependent. So this definition here is not correct. But unfortunately, it does appear in many textbooks of linear algebra. So let's proceed with proving a couple of theorems. And suppose we have any subset of Rn which has size greater than n, then we claim that this set is linearly independent. So if a subset of Rn is linearly independent, then it must have at most n elements. So let's prove it. So let's take V1 up to Vn plus 1 distinct elements of S. We know that we can do this because S has size greater than n. And by greater, we mean strictly greater. And let's form a matrix A, which has these n plus 1 vectors as column vectors. So this is an n times n by times n plus 1 matrix. And we consider the system A times lambda 1 all the way up to lambda n plus 1 being equal to 0. So this is essentially the equation lambda 1 v1 plus lambda 2 v2 plus dot 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 plus lambda n plus 1 vn plus 1 being equal to 0. Now A only has n rows, so its rank can be at most equal to n, which is strictly less than n plus 1. So the rank of A is n and is smaller than the number of unknowns. So this system here has a non-trivial solution. So we can find lambda 1 up to lambda n plus 1, not all of them equal to 0, such that lambda 1 times v1 plus dot 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 plus lambda n plus 1 vn plus 1 is equal to 0. But this exactly says that S is linearly independent, which is what we wanted to prove. And our final theorem says the following. Suppose we have distinct v1 up to vk elements of a vector space. And let's consider the set containing v1 up to vk. And let's suppose that this set is linearly independent. Then the theorem says that every element of the span of S can be written in a unique way as lambda 1 times v1 plus dot 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 plus lambda k times vk. So let's prove this. And just by the definition of linear span, every element in the linear span can be written in such a way. So the whole point of the theorem is that this representation is unique. So let's suppose that this is not the case, that we have an element of the linear span, and we have lambda 1 up to lambda k, mu 1 up to mu k, such that v is equal to lambda 1 times v1 plus dot 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 plus lambda k times vk, and is equal to mu 1 times v1 plus dot 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 plus mu k times vk. But now we can subtract these two equations, and we use the commutative and associative properties to get that lambda 1 minus mu 1 times v1 plus dot 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 plus lambda k minus mu k times vk is equal to v minus v, which is equal to 0. And then because S is linearly independent, we must have that all these lambda 1 minus mu 1 up to lambda k minus mu k is equal to 0. And now uniqueness follows. We get that lambda 1 is equal to mu 1, lambda k is equal to mu k, so we do indeed have uniqueness.